Alright, I've got an example where I'm going to calculate actually all I'm going to do is set up the integral that would need to be evaluated to calculate the electric field due to a uniform line of charge that is oriented at some angle with respect to the x-axis. So I have what I'm talking about drawn here. I've got the x-axis pointing to the right, the y-axis is pointing up, and then I've got my uniform charge distribution that is along a line that makes an angle theta with the x-axis. I've got my charge distribution drawn in red because I can. So the charge distribution, let's assume, has a total charge Q, and let's assume that it has a length L. And I'm just going to calculate the electric field along the x-axis. So I'm looking for the electric field, which is a vector, as a function of x, where y is already set equal to 0. So I'm going to set the whole problem up with that condition right from the beginning. So the field that I calculate will correspond to y is equal to 0. So let me just draw a picture of where I'm going to evaluate the field at. So this is my observation point. And now I need to construct the integral that will calculate the field at that observation point. So again, the way that we go about doing this is we know that the field due to a point charge can be written as this. So if I have a little piece of charge, call it dq, little piece of charge dq, and I know how far away I am from that charge, I can calculate what the magnitude of the electric field due to that charge is. And if I have a direction vector that points from the charge to my observation point, I can also determine what the direction of that field is. So what we have to do is we have to use this, which is only true for point charges, to figure out what the line is, what the electric field is due to the line charge. And of course it's erasing. So this is point charges only. So we use calculus to use that electric field equation, right, what the field is due to a point charge, to determine what the field is for a non-point charge. So the way that we go about doing this is, first, I just pick an arbitrary point on the charge distribution and focus on figuring out what the field is due to that point, and then adding up the contribution for all points together to get what the net field is. So I identify the piece of charge that I'm going to be looking for. I now need to write down a parameter that I'm going to use to identify that piece of charge, and this parameter needs to be something that will be unique for that piece of charge, and this is going to end up being my integration parameter. So I'm going to use the distance from the end of the point charge. The bottom left end of that point charge is at the origin, and any piece of charge on that line charge can be identified by this distance from the origin. So that's what I'm going to use. So L is going to have to be my integration variable. And that means that all of the stuff that appears in this Coulomb's law type of equation has to be written in terms of L if it depends on L. Alright, so I'm going to do the same procedure that I've done in class multiple times. I'm going to write down the position vector for everything. So I've got a position vector for an observation point that I need to write down, and then I need to write down the position vector for the source charge, which is this little piece that I'm looking at right here, right? This is the source charge. So the observation vector, the position vector for the observation point is just going to be, well, I need to specify, well, actually I've already got, I'm assuming that I'm looking at it at any point on the x-axis. So the observation point will be a distance x from the origin, and it is only on the x-axis, so it's going to be x times x hat. Alright, now for the source position vector. So this thing, this line charge is oriented such that it makes some angle with the x-axis, so the x component of the position vector is just going to be L, that's how far it is from the origin, times cosine of this angle, so that's the x component, and then the y component is L times sine of that angle. So there are the two position vectors, and really that's the hardest part. Once I get those written down, everything else is just the same procedure. Now, of course, we can, sort of try to understand what it is that we're doing, and that's what I'm going to try to do as we go along. So I'm going to calculate the displacement vector that goes from the source charge to the observation point. And that's going to be the position vector of the observation point minus the position vector of the source charge. Which looks like this. So physically I know that this vector that I have drawn here corresponds to the vector that goes from the source charge and points to the observation point. Right, so this is delta R source to observation point. And just by looking at that, I can tell that the y component for that should be negative, and I have a negative y component here. And I know that the x component is going to be positive in the case that I have drawn here. It'll be positive for all points along the line that are to the left of the observation point. So if the observation point was over here, then all of this stuff would have a negative x component, but this stuff would have a positive x component. And so I see that that actually shows up as well. The difference between the x position of the observation point and the x coordinate of the source charge is going to change sign, right? When x is equal to L cosine theta, I'm going to get a sign flip. So that actually gives me what I expect as well. All right, so I've got that displacement vector. Now I have one more thing that I need to calculate. Well, I guess I got two more things that I need to calculate. What I need is this r squared, and so I need to calculate what the length of that displacement vector is, and then I need this r hat, and that r hat will just be the displacement vector divided by its length. So once I calculate the length, it'll be easy to get r hat. So let me write down let me change colors here. The length of this displacement vector, which is r, is going to be equal to the x component squared plus the y component squared square root of. There we go. And r hat then is going to be the displacement vector divided by its magnitude. There we go. So I'm going to put it all together now. Come down here a little bit. The field due to just the piece that I have drawn is going to be Coulomb's constant times, I've got one more thing that I need to calculate, and that's dq. So I need to figure out how much charge is in that piece that I'm looking at, but that has to be written in terms of this integration variable. So I need to write this dq term, which is right here. I need to write that in terms of a dl. So if I look, this is a straight line, so the length of that little piece is just going to be dl. And if I multiply that by the line charge density, it'll give me the amount of charge that's in there. Now I've got the total charge of that line charge and I have its length, so the line charge density is going to be that total charge divided by its length. Alright, so now I've got the amount of charge that's in there. That is going to be, let's see here, dq is lambda dl. So this will be q over big L dl. And then I'm going to divide by, I've got basically three factors of r that show up. I've got a 1 over r squared from the Coulomb's law equation, basically. And then I've got another 1 over r that comes from the normalization of r hat, right? So I've got this one that shows up. So I'm going to combine those into a single term, and that should give me this in the denominator to the 3/2. And then I still have the direction piece that I need to tack on here. And so the direction piece is just this, is just the displacement vector. There's an x hat and a y hat. All right, there we go. So there's almost all of the physics. The last piece is put this all together and integrate it. So the field that I have written down here is the contribution to the net field from just the little piece that I have drawn here, right? So this little piece creates a field that points down like this. If I looked at the field due to this piece over here, it would create a field that pointed off like this. What I need to do is calculate all of those and add them together. So the reason that it's important that I write everything in terms of this integration parameter, or this parameter L, is because when I do the integral will basically account for the fact that I'm going to start here, then I'm going to add this, and I'm going to add this, and I'm going to add all of these pieces together, which are all going to give me fields that point in all different directions. But all of that's going to be handled automatically because I've written everything in terms of this L. And so the integral will account for all of that and give me the net electric field at that point. All right, so I need to get my integral set up with the correct integration limits. So the total field, or the net field at that point, and this will only be true for x and y is equal to 0, because I've assumed that when I wrote down my position vectors. The integral of all of this stuff and I've got the integral is with respect to L, so I've got my DL right in here, and I don't know, I guess, sometimes we'll make the mathematicians happy. We'll put the DL on the outside, so everything in between the integral sign and DL is the integrand. And the limits of integration are whatever L has to be in order for me to be looking at the bottom side of the charge distribution and then the top side of the charge distribution. And so when I'm at the bottom, L is equal to 0, and when I'm at the top, L is equal to the length of that line charge, which is capital L. So this will be from 0 to capital L. And there we are. This is the integral that would have to be evaluated in order to calculate the field along the x-axis due to this, this charge distribution. Of course, it doesn't look very good, but now it's just a calculus problem.